Alright, hi everyone. We're going to talk about matter today. So we are moving into our chemistry section of the class. And of course, first thing to talk about is matter. So chemistry is the study of matter. Matter is anything that takes up space or has mass. So there are things, you could list all kinds of things that would be matter. So maybe even stop and think, make a list of what is around you that is matter. So on that list, you might say the chair, a table, person sitting next to you. Those are all examples of matter. You might even say that air is matter. It still has particles in the air that take up space and have mass. An example of something that isn't matter is light and sound. If you want to go into the quantum mechanics of it, then it gets a lot more complicated. But it's a good thing sound does not matter otherwise. All of the yammering and talking that I do during a class period would smother you, right? And we don't want that. So matter is everything that takes up space and has mass. So when we think about matter, it's made up of atoms. Atoms is a term that was developed by a guy who was a Greek philosopher from way, way, way back. His name is Democritus. He did a thought experiment where he was just sitting around and talking and thinking to himself, hey, what if I took a piece of matter and I cut it in half over and over and over again? And he thought, hey, is it possible that I'm going to get to a piece of matter that can't be cut anymore? And he decided that, yeah, in fact, there was. And he called that piece of matter atomos, which is atom. It means that it's indivisible or uncuttable. It can't be cut in half anymore. So it's the smallest particle of matter. So his term, we still use the atom, but the model of the atom has changed over time, which you'll learn more about in chemistry. So what does an atom look like? It's kind of hard to really tell. So atoms are way too small to see with the eye, but if we could see them, maybe they would look like this, but probably not. We can see groups of atoms. Look around. Everything around you is made up of atoms. We have some instruments that can see single atom, like effects of single atoms, but really, what does an atom look like? That's a tough question. So groups of atoms, we call them elements. Elements are when they are identical atoms, which what I mean by identical is they have the same number of protons. So elements all have a unique number of protons. Okay. Atoms do not necessarily have the same mass to be the same element, but they do have the same number of protons. An example of an element is anything on the periodic table: calcium, argon, nitrogen. Notice that calcium and argon don't have any subscripts, but nitrogen does. Nitrogen exists as two nitrogen atoms bonded to each other in nature. So the formula for it is N2. Oxygen also does this. Hydrogen, chlorine, fluorine, bromine, iodine, they all exist in this, what we call diatomic state. Okay, so you don't necessarily just have free element, just a free atom hanging around. And many of our elements actually exist not as a free element in nature. They're usually in compounds. So some of our metals have to be in compounds as opposed to just a free element. We can represent atoms in different ways. So an atom of one element might just be single atoms. The diatomic elements have the same atom overlapping or attached by this little rod showing a bond. Now, there is no such thing as an actual rod holding together the atoms, so that is just a visual representation of a bond. But really, it's more like this. There's overlapping of the atoms' electron cloud. All right, so we can do pictorial representations. When you take elements and you start combining them, they form compounds. If you've got the different elements, they're bonded to each other. They're attached. Compounds are when you have multiple elements bonded. So example, well, they're not going to be on the periodic table, but they do have a chemical formula. Compounds have a chemical formula. That is the big key thing here. So some examples, NaCl, that's the formula for sodium chloride. We talked about sodium chloride in class today, or you're watching this tomorrow, so yesterday. H2O, dihydrogen monoxide, or water. That has a chemical formula. NaHCO3, this is sodium bicarbonate. This is baking soda. Okay, so each of these has a chemical formula. It's a compound. Okay, compounds are not mixtures. You can't separate them any further without changing their identity completely. You can't take the hydrogen away from the oxygen and still have water. It's not going to work. We can visually represent a compound by having two different shaded atoms. We can have them overlapping or with that little rod between them. Okay, this is called a ball and stick model, this bottom one. Alright, so let's identify some of these as elements or compounds using these pictorial representations. The one here in jar A, I see there's two of the same element attached to each other. Each unit, though, is the same. I would say this is probably an element, since they're the same atom attached. You're not changing the atoms. That's an element. Jar B. I see some gray circles and yellow circles. The gray and yellow are attached to each other. So that means different elements. So that must be a compound. In jar C, the grays are attached to each other and the yellows are attached to each other. This looks like it has two elements within the jar. Same for jar D. It's just the ratio of the gray to the yellow is changed. So we've got element, compound, elements, elements. Okay, so here's your answers. Element, compound, two elements, two elements. Alright, so we've got pure substances. That would be classified as an element or a compound. So pure substance would be the broader classification. You can't separate a pure substance. It is pure. There is nothing to separate. Okay? So elements, you don't see any other atoms other than these little blue circles that are attached. Compounds, yes, you have two different elements, but each unit is the same. There's nothing to separate without chemically changing the substance. So pure substances cannot be further simplified. We have mixtures. Mixtures can be separated, and there's an entire division of chemistry devoted to this separation science. That's analytical chemistry. Separations, it doesn't mean it's an easy separation necessarily, but it can be done, and the separation does not change the identity of each of the components within the mixture. Okay? So here's a visual representation. The yellows look like free elements. The red and the blue, they're attached, so they're a compound. So in this box, there's an element mixed in with a compound. You can separate all the yellows out, and it's still an element. You can separate all of the compounds, the blue and the red. They're going to come as a package. You're not going to get all the red elements out. You have to take the red and the blue together. Okay? So the separation can be done. So let's look at these jars again and now identify them as pure substances or mixtures. So jar A, we said was an element, so that's going to be a pure substance. Jar B, I think we classified that as a compound. Compounds are also pure substances, even though there are different elements in here. Each of these molecules or units is the same. That's a pure substance. Jar C has two elements. You can separate out all the yellows from all the grays. So this is going to be a mixture. Same deal for jar D. You can separate all the yellows away from the grays. And you can classify that then as a mixture. So we've got jar A was pure, jar B was pure, and the last two jars were mixtures. There's different types of mixtures. very broadly, we'll describe them as either homogeneous mixtures or heterogeneous mixtures. In chemistry, you're going to go a step further and classify them into other categories. But homogeneous mixtures means that you have a substance that is completely evenly distributed. All of the particles within that mixture are even. So if I take a teaspoon and scoop out some of the mixture, I'm going to get the same composition as I would if I stirred it and scooped out another bit of that. So an example is apple juice. Apple juice is pretty much the same throughout. All of the substances are completely dissolved. You don't see any particles floating around, usually. Okay, so, but definitely the apple juice you get at the store. I'm not talking about apple cider, but it's pretty well filtered. You have just a homogeneous mixture. Heterogeneous mixtures, this example is a rock, but you can also have other phases of matter too. You can see the different colors within the rock, which are indicating different composition of that rock. It's not evenly mixed. You could look at if you took a cup and went and filled it up down by the river, down by the Scioto River. Most likely, that's going to be a heterogeneous mixture. There's going to be things floating in the water. There's going to be mud that settles out over time, or silt. You might get a leaf. So that is a heterogeneous mixture because the composition is not evenly distributed. I'm not describing how much of each component is in the mixture. I'm just saying that the components are either evenly mixed or unevenly mixed. So that is homogeneous and heterogeneous mixtures. Whoops. I'll fold this over. So, what kind of substance is each of the following? We have hydrochloric acid. Well, you haven't had a whole lot of experience with hydrochloric acid, but it's hydrochloric acid dissolved up in water. If I gave you a jar of hydrochloric acid, it would look like a jar of water. So what do you think? Is that a pure substance? Is that a mixture? And then what kind of mixture is it, if it is a mixture? Tap water. Water that comes right out of the tap. What is that? Is that a pure substance or is it a mixture? Muddy water and sodium. So pause your video and think about it. Okay, well, hydrochloric acid, I already just said that hydrochloric acid is usually dissolved up in water, right? So hydrochloric acid, so what I'm telling you is not what I'm seeing as my answer. Hydrochloric acid has a formula, and since I'm not saying anything right here that is dissolved up, I'll do it two scenarios. Dissolved in water, not dissolved in water. If it's not dissolved in water, hydrochloric acid still has a formula, and we would call it a compound. Compound, the formula, is HCl. If it is dissolved up in water, though, it looks like a jar of water. It's completely evenly mixed. It is a mixture, and it is a homogeneous mixture. There you go. Hydrochloric acid could be both a compound or a mixture, depending on what scenario it's in. All right, tap water. So tap water coming out, is it a pure substance? Unlikely. So the tap water that is coming out of the tap has lots of things dissolved up in it. But ideally, everything is completely dissolved and you can't really see particles floating around it. If you can, well, maybe it's not the cleanest tap water. So it should be a homogeneous mixture. Water has a lot of stuff dissolved up in it, but it should be dissolved. And ideally, it is a small quantity of whatever is dissolved in it. So there's minerals, there might be all kinds of other things dissolved in your water, but it's usually at such a small concentration that it's not going to be harmful. At least, unless you're referring to a few months ago when the water in Columbus it had too high concentrations of, what was it? I can't remember. Nitrates, maybe? I think nitrates. There's a lot of nitrate in the water. It was coming from runoff from some storms. And they warned the entire city, do not drink the water if you are elderly or have young babies or pregnant. So, but then they fixed that. So tap water should be homogeneous. Muddy water. You probably can see those particles, and I used that as an example just a second ago. That's a heterogeneous mixture. The particles are suspended in the mixture, not completely dissolved. All right, last one, sodium. Where do you know that is located? I believe on my periodic table. Sorry about that. Sodium is on the periodic table. It's an element. So it's definitely a pure substance, and it's an element, okay, on the periodic table. Nice job. You got them all right. We'll do a lab later, I think. That's the end of our video.